and talk about data science warm-ups. It's mostly about data wrangling, data manipulations, cleaning, or diagnosis, and data transformation and conversion. All those kind of stuff. All of those are considered part of the data pre-processing and data cleaning. Nowadays, people use a fancy word, data wrangling. Wrangle with data. It's like rustling with the dirty data and try to make it clean. Well, it's a trend. It's a buzzword. So, so we're gonna start because I try to shorten the time of lecture so that you can spend time on reviewing other videos and spend time on the more interesting things that are recorded in video and reading the books and practice hands-on. So I will not review, if not necessary, I won't review the previous lecture, right? Make sense? Because you all can refer back to the video to look at what was discussed if you forget anything. So there's no point to really spend time here to review what was there, unless it's very, very relevant. Unless it's something that's connected to today's, I will review. So let's see. Now, here is a list of topics we'll talk about. All of them are considered part of the data pre-processing. In the hands-on part, in the demonstration part, I'm going to use this data set. Let me change it to laser. Okay, I'm going to use this data set, default one. You can download it from Blackboard. And there are 3 data sets available for download. Make sure that you put the right one, default, otherwise the code will not run. We're going to talk about data transformation. Mostly it's about variable scaling. Several of you already have a few questions about data scaling, and I assume you'll be very familiar with these. Even if you haven't been through any business analytics class, I'm sure in some of the other data analysis class you know about these standardization and range normalization. We'll just briefly revisit them. And I'll talk about transforming categorical variables. I don't think these will be strange to you. And last but not least, we'll visit a few of the most frequently used linear algebra aspects and matrix notations and Python implementation. This is so that you can use the cheat sheet that I create for you to guide you through implementing, logistical regression, add-a-line model, and neural networks, and later some other text mining stuff and unsupervised models. So these notations will bridge the linear algebra and Python implementation. And it's always good to understand the connections between them, even if you don't necessarily have to remember the details, but being able to understand them will help better implement them faster. All right, so let's go. Obviously, data pre-processing is important. I'm sure many other professors have told you about that. And this is especially true in business. As I said, in computing engineering, problems are more clearly defined. So the data are cleaner. And data cleaning, data pre-processing, a lot of them, or data, putting the data together, collecting the data, they are not typically considered as part of the project. It's considered as a motivation part or outside the scope of the project. The project is, in computing, is typically the problem itself. But in business, it's quite different. As I said, a lot of them, the data were created without having in mind any future project related to data mining or data science. But now, data science is helpful to leverage those data that are sitting there, not generating any more business values. So all of those data are summoned here, but they are not properly stored. So data pre-processing is especially important in business projects. And without doubt, there are tricky issues to deal with in business. Common tasks performed in data pre-processing in business particularly. Missing values is a big one. I will not delve into missing values, I'll simply mention it. And throughout the course of this class, we will not deal with missing values. The reason because several other courses may have already talked about it. The missing value problem is prevalent. It's not unique to specific algorithms. Although some algorithms are more immune to missing values than others. Like decision trees are more immune to missing values than regression-based or neural networks. More intuitive models are more robust to missing values. But it's a topic that many courses talk about. You probably have had a good understanding about them. And dealing with missing values involves several aspects that are not trivial, but also they involve a lot of details. We'll take a lot of time from this course, and we don't have those time. So that's why. If you're interested, refer to the book in DKD about the more of the conceptual side of the missing value problems, and about Python implementation in dealing with missing values, refer to GML, I think chapter 4 or something like that deal with data pre-processing. There's an important subchapter about missing value imputation. So that's it. What I will focus mostly on is erroneous labels of the columns. This is more of a data cleaning. You would think that this is barely even a problem. Every table has a header. Every database has a column name or a field name. That shouldn't be a problem. But in terms of machine learning, because a lot of data are brought together, which will typically become a large data set, and multiple groups of people are working on the same thing, but they have different backgrounds. So even with typically non-confusing column names, the interpretation could become problematic just because some common labels makes more sense to some others, to the finance department, but not to the technical department. So you can imagine a misinterpretation of a column could mislead the design of the model building process. So every time you start a new project, it's highly suggested that you review the column labels and redefine them or modify or replace them to become something that you or your group will be familiar with. If anything is misleading, change it to something that's more straightforward. Avoid using fancy names for the column names, just to make sure, because data mining projects are, a lot of times it's collaborative. It's multiple departments collaborating together. You want collaboration. You want better communication than just trying to be fancy. I won't go too much into details. We will deal with them if the data set has this kind of problem. But it's quite intuitive, I will also talk about, this is erroneous labels in categorical input variables, or categorical, typically target variable if they are categorical. it's not going to be it's not going to be too much of a problem, because target variables are typically a very important field that carries key information about the decision. So it's typically error prone. But input variables can have various kind of issues. Definition of some of the labels may not make sense. There may be overlap between some of the labels, leading to misclassified data points in terms of labels. But to deal with these problems is straightforward. There are quick tools to do that. We'll quickly talk about those. And there are sometimes data recorded in a format that is not optimal for data mining purposes. For instance, a date variable recorded as string typically is fine if it follows a standard format. But look at this. Take this example. 2019 131. What is it? Typically there are 8 digits, not 7 digits. But sometimes a digit is missing simply because, you know, the month, for the month, between January to September, if the month is recorded as numbers, as integers, the leading zero will be dropped if it's processed as integers. So that will lead to this kind of incompatible data format. The better way to record date is always to record it using the date format in the in whatever the data architecture that the data is stored. Date variable programmatically, it requires some exercise, but it's not tricky. It's not too much. It's not very tricky. It just requires some exercises. So avoid using incompatible date format to record the date. It's better to use the date type variables to record the date. Erroneous values. Erroneous values are those values that involve some error. If those values that involve error are not outside the boundary of the normal range of that variable, it will be difficult to detect. So you would just have to hope that the data collection or data capturing mechanism is robust. It would not lead to, or if any human data input is involved, you want to make sure that the system that was used to accept human input is more robust to very crazy number input, or in number fields, letters should not be accepted. You hope that the information, the system will reject values that are not suitable for that variable. So for the erroneous values, typically we're talking about interval variables, continuous variables. For those variables, if the value involves some user input error and the value become too large or too small, we can use the straightforward methods to detect them. Let's see. And here's a very interesting question. So let's talk a little about age. Age variable is a demographic variable. Any data set about humans, the customers or employees or users or different accounts, they typically will involve age. Sometimes age is not collected because of privacy concerns, but a lot of other cases age is collected. And age is, a lot of times, it's a piece of useful information to predict the behavior, just because different generations behave differently, and there are also cultural issues. So think about this: a data set records age, and let's say this is a banking data. So banking customers has an age column recorded. John is 45 years old, Susan is 33 years old, such and such. What can go wrong with age? Let's do a quick zoom. The question is, what could go wrong with an age variable in a typical consumer data set or user kind of data set? I'll see if, let me stop the screen share. I'll see if I can put you into the same groups from last time, but if not, let's see. Yeah, I think new group will have to be created. Let's do 5 teams. It's going to be different groups. So let's see. All right, we'll start the breakout rooms.
I still confused for this question. So what's mean by age problem?
I think it's
Wildly.
better. I'm sorry.
Go ahead.
I think it's better to store the age variable as date of birth, because now customers' age changes all the time. So if you just store them as age, you will have to update the column now and then. Otherwise, some data will get outdated.
Okay. Makes sense. So what can go wrong with, I think,
PowerPoint showed. That's it here. What do you think? That is our year and month and the date, but if the month is not showing 2 digits, when they do the calculation to calculate the age, and the age will get the wrong result.
I don't think that's related to the age variable, because if you were to record the age in a data set, then we will, like, if talking about the months and everything, that will be in a different column. That will be in the date of birth. So I think the age part and the date of birth part would be 2 different variables. What I think would be the problem with the age variable would be, like, we could either keep it as a continuous variable or categorical variable.
Oh.
Do you guys know, like, what continuous variables are, right?
I think that depends. Like, age can be both type of variables, right? Can be categorical and also.
Yeah, I think that's the main
continuous
issue, right? Like, that is the issue. Like, usually we have to associate one kind of variable, like whether it's one kind of data type of variable, like it would be the categorical or continuous. But I think that's the issue with an age variable, whether, like, we are not so sure whether it's going to be a continuous or it's going to be categorical.
I think that sometimes if we use age as a categorical variable, we may like make the age to separate in different period, like the age between, like, from 20 to 30, 30 to 40, and 40 to 50. And so you can have the 4 or 5 categories and use in this way.
Yeah, agreed. But like that's the, I mean, that is the main issue with this. And that's what I feel is the main issue. Like when you have two different kind of variables, I mean, two different data types of a variable.
I've got a little experience with Python.
Yeah, me, I mean, I have zero knowledge about Python, so.
Yeah,
I've taken what's that class? R. I heard that's pretty similar to Python in terms of like coding.
Yeah, I think
Yeah.
Python is fun.
Have you guys tried Python on Mac? I think it might have some problem. Is there anyone that uses Mac?
I've tried Python and
Pretty quiet here. Well, anyway, is there any confusion about the problem?
Yeah. We were talking that maybe the issue with age is that it could be confused to use just a number, since if you compare 80 years old versus 5 years old, then you could have the feeling that 80 is better than 5. But so maybe it could be better to work using range.
Okay.
You know.
Data type. All right, we're all back. Some of the groups are really on the point, while some other groups have trouble getting sort of the meaning of the question, really. It's kind of a think outside the box problem. So it's not immediately intuitive. It's not an intuitive issue. So let me talk about that. Let me share my screen here. And in the meantime, we can also talk. So in terms of age, it's straightforward. Age is, how old is a person in the database. So here, in terms of potential issues, one really have to think about the age as a piece of information to describe the person. And as time goes on, does it lose the meaning? So that's kind of, typically we say, in database are good in recording transactional information about this customer in a current event or in the current state. So, purchase information or basket or, shopping basket information. It's about this shopping experience. And after this shopping is done, this shopping event is over, it's a fixed event. It's an event in the past and the information is recorded. Everything is good, everything is fixed, that's fine. But information about age, it needs to be adaptive to time. Think about this. John is 35 years old as of today. Next year, his age should be updated. However, age column in a data set, in a typical data mining data set, doesn't change. So this creates a problem as to implement the model on a set of customers to try to predict the behavior and try to intervene based on the prediction results. You can think of numerous examples of how this can be a problem. But if you think about the fixed status of the data and information in a data set, then age quickly becomes an obsolete column to the customers, especially if those customers are still relevant and you are going to implement and develop and implement models to intervene about the behavior and to predict the behavior and to intervene with the person that you try to predict. There are numerous examples that you can think of. There are policies that depend on the age and very exactly depends on exactly what the age is. The financial consequence can be huge. The example on the screen is the United States Social Security Administration. They govern policies about how Social Security benefits, which is part of the retirement benefits that retired U.S. citizens can enjoy, can benefit from. They require that full benefits can be received only after the retiree has passed 67 years old. But they are eligible to start receiving because some retirees simply need the income, right? So it's part of the duty of the government. But the administration allow retirees to receive benefits earlier. They can begin receiving benefits in the age of 62. So if John or Mary, anybody, his data started to be collected at certain time, and his or her age is 64. He or she is not yet eligible for full benefits. Whenever benefits are sent out, a discount is taken because he or she is receiving the benefits earlier. Now, given, 64 years. So in 3 years, the benefits penalty should be gone. However, if the data set's age column is not updated in 3 years, the same person will continue to receive penalty. And this is a huge consequence, a huge damage to a lot of things. And it's a problem that may be hidden and hard to diagnose, because if we assume the data doesn't have a problem, then it's a design problem, actually. It goes to the root of the design of the data collection and data storage. So this is a bad practice for variables such as age that needs to be routinely updated, and which is also not straightforward to update. It's not like a year variable. It's easy to update because of the standard calendar time, but age gets updated differently depending on a person's birthday. Everyone's birthday is different, so you can't use a stored procedure to do that very quickly without having the exact birthday information. So, but given that you have birth date, why do you even need a column for age? It's better to store the birth date, and some of the groups has discussed this, which is great. So it's better to record the birth date as a date type variable, and whenever age is needed, you simply calculate the age on the fly, which is a very straightforward task. So that would be a word of caution. Any questions? Good. Any confusions on this? Other than that, if age is calculated and not stored inside the database, but calculated because for the purpose of training models, then there's no problem. Anything else to discuss about age? No? We're good? Great. So let's see. Data pre-processing. I talked about several typical problems. One is the labels that are labels of categorical variables, input variables. When I say inputs, I mean input variables. Labels of the categorical variables are misclassified, which can be a problem of overlapping categories. You know, if there's a category which is Asia, but then Japan is another category, then Japan should be part of the Asia category. So that's a misclassified. And this problem happens probably because of a free style input. The data can be input from user, not automatically generated, but then the user didn't think of the broader category, wasn't aware of that. So that rare category is kind of created by a user input error. And for that, we can use simple, we didn't even have to use a bar chart. We can use summary statistics tools to quickly identify those rare categories. And you can look at those categories that has only one or two cases. So those are user input errors. And you can quickly single them out and correct them. There are also errors that happen in continuous interval input variables. And if these values are not outside the boundary, are not outliers, they are difficult to detect. But if they are outside the boundary, you can use simple graphical tools here. We'll quickly demonstrate a few of them. Let's see. So, I don't know if you remember, several of you did advanced programming with me. How to get the statistics and labels of a categorical variable in Python by using the NumPy series. If it's a series, let's say, I don't know, S1. If it's a series, to get the, and if it's a categorical variable, let's say gender, how to get the number of males and number of females statistics from series. It's a method of series. Do you recall? If you don't remember, let me remind you. It's value counts. So in Python, you have a series, which is a column of a data frame. You call the value counts method without any arguments, and it will print out labels and the counts. Label and count, all the labels printed out with the count of number of cases of that label in that variable. And if you identify a label with only one or two counts, then you can closely examine the label and see if there's only any user input error, or if there should be overlap between the labels. So you can use replace command to replace method to replace the misclassified labels. For let's see, let's move on to the input variable errors. For a continuous variable, if an erroneous value is outside the normal bound or normal range of the variable, it's considered outlier, and it's because of a user error outlier. And you can, for continuous variable, you can quickly create a histogram or a distribution chart, right? And you would typically, you can do a histogram, a lot of bars, or you can do a hist plot. You can use two packages to do that. for matplotlib dot pyplot, you can, this is assuming that I have imported as pyplot, you can use pyplot.hist command with some, with the data or the x variable specified and the data variable and number of beans and other properties. Or also you can use, if it's a NumPy series, then you can simply use a method of the series is, I think it's plot, series.plot.hist, and specify additional, properties of the histogram to do that. But you can also use another package, which is a built-on of the matplotlib, which is the Seaborn. Seaborn graph it looks better, and it requires less programming, and a lot of times it works well. Import Seaborn as SNS. You can use this plot and specify the data and other things. So using statistical, summary statistics or visualization to detect erroneous labels or values in these type of variables. Any questions? Let me erase some of these. And we'll do some demonstration and hands-on practice to refresh about these. Okay. Tools for data preprocessing in Python. Typically, we use Pandas, and NumPy functions are occasionally used. For data preprocessing, typically Pandas. I would prefer Pandas. It's a lot better. Has more metadata information. It's more intuitive. It's limited to 2D, two-dimensional data set. But in data science, we typically are dealing with two-dimensional data sets. We're not dealing with high-dimensional things when we pre-process the data. So it's typically good. Pandas. I don't know why the pandas doesn't look like a panda. It looks like a bear. It kind of offends me because I'm from China. I have requested them to change the logo, but they ignore me. Anyway, well, at least you can use black and white. It's more like giant panda. It's not even a small panda. Small panda has a long tail. Anyway, it's kind of wrong. But that's it. I hope they can change it. Any questions on this slide? Good. And let's see. Okay. Now, data transformation. We're talking about more standard transformations. So it's more related to standardization. And when we talk about standardization, we need to standardize something. And we typically standardize two statistics here, the mean and standard deviation. And they go together. So the mean and standard deviation is a way to summarize the distribution of a variable without having to, to spell out the specific numbers. By using the mean and standard deviation, you can summarize the typical range, the variance, the spread, and the location, or the central location of the variable pretty well. But there are other exceptions where these two statistics are not enough to summarize a weird distribution. Here a few notation, a few comments about notations. Sample mean, we typically use X bar. you may be familiar with mu. But we don't use mu to describe sampling. Mu is a population. So you will almost never see mu in data analytics, because we're not dealing with population data. We only have a sample, even though it may be very large. So X bar, we use a bar to denote the mean, and this should be very familiar to you. If I want to describe what is a sample mean, it is the sum of all the X inside the sample divided by the sample size. We will use the sigma summation size quite often to denote how some of the quantities are calculated. S is standard deviation of the variable in the sample. You may be familiar with sigma, small sigma. We don't use that to describe the sample standard deviation. That is for population, so we don't use it. We don't use it. The amount and spread. I want write the formula for that. Standard deviation describes how spread out the values are for this variable. So sample mean is supposed to measure or to estimate the center location of a variable. It typically works well, but not always, as you know. It doesn't work well for skewed data, and in real life we have many variables that are skewed. We have income that is skewed, right? And we have a lot of things that are skewed. For skewed variables, the mean is not the best summary of the central location of the variable. For skewed skewed variable, median is a better description. Median is the point where half of the sample has a value that's larger than the median, and half of the sample has values that are below the median. That's a central point. That's exactly what it is measuring. Here is a skewed distribution. The scale is harder to see, but it's between 0 and 10, so it's equal interval, and the height is the probability. Assuming that this variable can only take integer values between 0, 1, 2, between 0 and 10, can you roughly estimate the mean of this variable based on the shape and based on the scale? Who would like to give me a quick guess?
Would it be to the right because it's skewed, right?
So give me a number. You give me a number. So this is 0, 1, 2, and up to 10. Right. So give me a best guess.
Number 2.
2. So this is close to X bar. Is that your guess? Yeah, I would say it's between 2 and 3, and close to the 2, but it will be beyond 2, but not lower than 2. But I don't know. No one has to calculate to be sure. But based on the long tail and fairly smooth transition to the tail and thick portion beyond value 3, the mean will be pulled up. Right? The mean is biased toward the tail, even if the bulk of the sample is within this region, and this region is quite bell-shaped. Let me change the color. So this region, it's sort of like a bell shape. This region is the bulk of the sample. If there's no tail here, then the mean, median, and the mode will be located on the same value. It's 1 point something here. If they are symmetric and they are smooth without tail. But with the tail, it's quite skewed. So the mean will be biased toward that. And the median will be much less sensitive to the extreme values and the tail. But it will still be pulled up a little bit. So the median will be somewhere between the mode. This is the mode, is where the most frequently happen value take place. The median will be between the mode and the mean, roughly. So, great. And because of this property of the mean and the median in skewed distribution, median is a better summary. And median is a better representation of the center of the variable. Missing value imputation with a statistic. If you have to use a statistic to impute the missing value here, the variable is interval but has a long tail, it's not symmetric, it's skewed, then median replacement will be a better strategy than mean replacement. Okay. Make sense? Yeah? Let's move on. Okay, let's play with the data a little bit. So this data set is the default one. It's from a retail bank. It's a subsample of a larger sample. I've taken a subsample just to make it simpler and make it more fun to play with. It describes customers of the credit cards of this bank. And it includes basic account information as well as the activities in 5 months. And each month is recorded as a separate variable. So it has statement amount, it has payment amount, it has payment status, whether or not there is any late payment, as well as the other information about the bank, about the account, credit limit. It even includes a year of birth, so we can calculate age based on that. The target variable is whether or not the customer defaulted the credit card account in the 6th month, following the 5 months that are recorded in the data set. This particular data set has 1,000 rows and 22 columns, including the ID column. Right. If you haven't downloaded this data set, you can download it now. We'll start playing with it, as well as the Jupyter Notebook. You can download the Jupyter Notebook and launch the Jupyter Notebook. We'll play with it. If you want to follow along with the demonstration, you can do that. Okay. We need more time? Or we can move on? Do you need more time? No? Good. So let me move on. A few things to talk about by using this data set. So transforming variable in terms of the scales. I'll briefly talk about why scaling is something that we must do for some of the models, and why. Scaling is necessary for those models that is complicated and has a lot of coefficients, parameters, and because of that, the model becomes complex. It puts more burden on the numerical computation to optimize the coefficients. And better scaling will be very helpful for those models to converge and find a solution. And here's why. Imagine that, so in this data set, there are two variables. There is a variable that is credit limit. Credit limit records the, everybody knows, I think, is the amount of money that you can borrow by using the credit card. So amount of credit you have, or amount of debt that the bank is willing to take from you on this account on a cumulative basis. The range of this variable is between 0, and I can't believe someone has a credit limit of close to $0. And what is then the point of having that credit card? That part I don't know, but I know that this data set is real. So, but needless to say, this variable has a long range. It has a range between 0 and almost 3/4 of a million local dollars. Local dollars have a lot of inflation, I guess, and a typical credit card has, the mode is close to 80,000 or 10,000, 80,000 local dollars, but it goes up to 750. The range it goes up to 750, but I didn't make a graph that long because there are bars there, but it's barely visible. The bars are very low. It's a long tail. So I cut off on in this graph on 600, so half a million, close to half a million. There's another variable, year birth, that has a range of 50 years from 1940 to 1990. These two variables, I've plotted them here. These two variables have different ranges, and 1 unit of difference in credit limit it carries very different amount of information in terms compared to year birth. So is $1 of difference in credit limit even matter anything? Barely anything. Just because, $1 may not be able to buy anything in that country because of the financial system that works. Here, typical customers of credit cards have a large range, so $1 may not be as important. But here, 1 year of difference may be quite significant. People who are 49 years old versus people who are 50 years old may have quite significant, behavioral changes, behavioral differences. There are not quite two different generations yet, but still, apart from a year, they receive different, different cultural background, cultural shifts happen between a year, and things like that. So 1 unit of difference for each of these two variables carry different amount of sort of variations to the customer that we're trying to describe here. So you cannot assume that the two variables' original range is equal. And also, when you try to analyze the relationship between the input variable and the target variable, here I've chosen one variable which is not exactly the target variable here, but it's a variable that we can analyze. It's a paid 5 variable, which is the payment status of the 5th month. And let's take a look. I plotted a scatter plot of each of the two variables with paid 5 on the y-axis, and you can see that the y-axis has the same scale between the two graphs, but on the x-axis of the two graphs, the range is quite different. The range that the data represents are different. that corresponds to the original range of the variable. You can see that the line has fairly similar slope, even though they are in different directions. But on the absolute value side, the magnitude of the correlation between the pair of variables in each of these graphs are quite similar. So maybe you can say that the correlation are quite similar. The correlation between each pair of variables are quite similar. And you're able to see this because we squeezed all the points into these maybe 2 inches. This is a 2-inch screen space of pixels. I squeezed this long range, almost 3/4 of a million units into a standard screen size. But I squeezed these 50 years of data into this standard size. On the standardized scale, sort of, the graph scale has been standardized because of the same size of the graph on the screen. We can see that their correlation is quite comparable. But imagine that if I zoom into the original scale of the credit limit, this graph will be super long. If we keep 1 unit as taking the same space on the screen, this graph cannot even put into this screen. It will be stretched out. The line, you can barely see a slope of the line. So that would be, on the intuitive level, that would be the disadvantage of working with arbitrary scales of the original variable. And that's the reason why we need to scale it. After standardizing the variables to have the same range, we can cross-compare the properties of the different variables. We can put them on the same scale to compare. So that's the intuition behind rescaling the variables. In terms of having the same range, that would be the min-max scaling, the min-max normalization method. Okay, if you have downloaded the notebook, it's here. If you have downloaded the notebook, you can run some of these codes, and we can take a look at how these graphs are generated, and import some packages for now, and make sure you have the data set and put the data set in the directory in the directory of the Drupal notebook. All right, so the data is read. So we'll make a histogram of the credit limit. Histogram. I'm going to use the series method. Well, let's take a look at the original scale. I will get the description, the descriptive stats of the series, and only take the min and max. Right? Only select this to slice only the min and max. Statistic. So the mean value is only 10,000. The max value is 3/4 of a million. Right, and then make a graph. I'll make a graph object, including the axis. I'm using the subplots here. It's quite straightforward. It's quite easy to. It's versatile, whether or not I want to create only one graph or 2 subgraphs. Then here I use Seaborn to create a fairly elegant graph without too much effort here. And I use number of bins as 40. I don't want to plot the kernel line, the sort of the continuous distribution. I only need the histogram. So the kernel line, I turn it off. And the rest of it is more of the labels, and I limit the range to be 500,000 or slightly over 500,000 because of the low bars on the string value. I don't want to see them. and to, once I change the X limit, I need to change the ticks and tick labels. And after that, the X and Y axis variable labels will be added automatically. So that's a simple, quick graph. It's exactly the same as the one in the slides. The same thing with the other variable, your birth variable. Then I'll make a here. I'll quickly implement this, the scatter plot. The color is green, and so it's a scatter plot between paid 5 and credit limit on the x-axis. Not adding too much other properties here. The scatter plot will put the points in there, will size it appropriately, and also plot the fitted line here. I didn't specify I want the fitted line. It will be automatically created. So that is that's a rag plot. Sorry. So here I'm using a rag plot, not a scatter plot per se. Scatter would be the scatter doesn't plot the fitted line. Rag plot will plot the fitted line. All right. Any questions for these columns?
What does scatter underscore KWS mean in the scatter in the reg plot?
Huh?
What is the last wording scatter underscore KWS? What does it mean?
Okay. KW is keywords. So you can specify additional keywords as dictionary format and pass it to scatter keywords. These keywords will change the property of the scatter plot per se. Here I'm changing the size. I think it's the size. I'm changing the size of the dots to be 15. Right? If I change it to be larger, the points is bigger. So that's the size.
Thanks for that.
Yeah. There are additional properties that you can set. You can refer to the documentation page.
Can you please repeat the difference between scatter plot and a reg plot?
The difference is not quite. I think the scatter plot, there's a scatter command in matplotlib. The scatter plot, so it's under the matplotlib library. It simply plots the points. It doesn't create or generate the fitted line here. The reg plot calculates the underlying linear regression between the x and y, and then fit a fitted line on the screen so that you can better see the correlation. So that's the difference. That's not too much. Reg plot is more effortless. You only have to write a few parameters, and the plot will be quite elegant. So that's the only difference.
Yeah.
Yep. So great. Let's move on. So this is better scaling of for the time sake. We'll skip the breakout room. Now, to scale the variable to have the same, same property, there are two common approaches. You must be familiar with this. One is z-score standardization. I typically refer to it as z-standardization or z-standard. It is to standardize the mean and standard deviation of a variable. So by the end, each of the variable will have the same mean of 0 and the same standard deviation of 1. It doesn't mean that they will have the same shape. The shape will not change. It is simply to have the same two statistics across all the standardized variables. Students ask me, which one of these two approaches are better. There's never a competition for that. anyway, the two scales a variable to different standards. It doesn't make it a good or bad. For most of the models, they are equally good. But for a neural network type of models, min-max normalization is better because it squeezes the values between 0 and 1, and that is quite aligned with the early generations of the activation function of neural networks. So that's why it's more preferred. And after that, even though that this becomes less relevant, I guess the convention remains that for training neural networks and even the deep nets, you would typically scale the values to between 0 and 1 using min-max norm. And the implementation is quite similar across the two methods. For other models, like regressions or other models, you can either use both. You can use both. You can either use one or the other. Z-score, statisticians may be more familiar with Z-score standardization. So that's something to keep in mind. Yeah, so this is categorical. Any questions about scaling? Great. So data transformation about categorical variables is it's not straightforward. It requires some care, but once you understand it, it's not going to be a problem. Categorical variables have several features. Categorical variables are those that we use that to describe those that have a limited number of unique labels. For example, color, direction, or a variable that has a long list, which is states and 51 labels. These kind of variables have labels that are texts, color, direction, north, south, west, east, and states. They have text labels. You can't even convert them to numbers, so you can't simply include them in a model. Machine learning models typically take numeric values only, so we need to convert it. Well, we can assign arbitrary values to it. We can assign red is 1, yellow is 2, so we go with the rainbow color sequence. That should make good. Well, the model will not complain, but your boss will complain. I think it's not the right way, and even I think your boss will recognize it. So be careful. It doesn't make sense because these arbitrary values, machines will take it seriously, although you don't take it seriously. So I have to have a better mechanism. Because the labels are not comparable, we have to use separate columns to record the indication or the existence of a label and the non-existence of the others. So we use the columns. You will use the flag columns, right? We call them flag variables. There are different terminologies. Some call them dummy variables, binary variables, or flag variables, or indicator variables, different kind of names. But sometimes we use binary to refer to those variables that are not 0 and 1, but simply having two discrete labels, like gender, male and female. That's binary. Flag variable is typically reserved for having 0 and 1 values. It's a flag. Flag is when its value is 1. And that when value is 0, it's not flagged. So we use flag variables. To convert a categorical variable that has k labels, we when k is greater than or equal to 2. So gender is a special case. The binary categorical variable is a special case. For those variables, we need k-1 labels. Marital status here has 3 labels. It has married, single, and other, I think. So those 3 labels are not comparable. You can't say one is much better than the other. You can't rank them. So that's why assigning arbitrary values do not make sense. I think we don't have to discuss. I think this is quite straightforward. If we arbitrarily assign 3 to married, 2 to single, and 1 to others, then we're assuming that married is 1.5 times better than single, which kind of makes sense because, you know, being married might be better than single. But anyway, depends on. Just kidding. And this is also assuming that being married is 3 times better than the other, which is not neither single nor married. There's a category which is divorced. There's a category that is without, but here in this data set, it's not being recorded or differentiated. We can't say that being married is 3 times better than other. So that's why this mechanism doesn't work. The only thing that will work is to create the flag variables. And I think you have worked with regression models, and creating categorical variable must be a topic of that part of the discussion. So I won't talk too much. We'll just use this as example. We use the example data set on the right, where 3 cases, or 3 customers. The first customer has a status of others, and if we choose these 2 labels to create the flag variable, then we have married and single flag variables. For a customer that has the marital status of others, its values would be 0 on both flag variables, which means neither or. This customer is neither married nor single. This customer belongs to the other category, right? And for a customer that is married, then the married flag will be flagged. We'll have an indicator of 1 and 0 otherwise on the single. And for somebody who is single, the married column will be 0, and the single column flag variable will be flagged. I believe this is very intuitive, so we can move on. Any questions? In Python implementation, if you take a closer look, if you decide to take a closer look at the data, you can use the Pandas method, get dummies, to create the dummy variables. It can help you eliminate one of the columns, which is great. It can also help you arrange the labels, the column labels, so you don't have to deal with the column labels. That's better. You can also specify a prefix to the flag variables to better organize the columns. So by using get dummies is a good tool for anything that is for any categorical variable that has more than 2 labels, like marital status have 3 labels. This is included in one of the tutorial videos, but I'm simply going to write it down here. Get dummies. I think it's dummies. Plural. Get dummies, and put the data in here. It takes 2-dimensional data, so it can you can put several categorical variables here, and it will transform every categorical variable and put all the flag variables side by side and return it to, and specify the prefix of the labels for the flag variables, and specify to drop the first. Then you can get k-1 flag variables. So these are for those cases where k is greater than 2. But when k is equal to 2, you can use a shortcut, sort of a more simpler code. You can simply use a comparison command in Python, and it will return true or false. If it's the same as a label. We use gender as an example. If there's a gender variable here, we can say typically gender is a series, so we need to get, if the data frame is imported as data frame, we have to identify the column as a series, slice or index the gender column, and then double equal is comparison, double equal female label. So for every row, it will compare every element of this column with the label. If the value is female, it will return true. If the value is not female, which means otherwise it's male, it will return false. And then you use an additional method to convert it back to flag variables. As type specify integer, and it will be converted to flag variables. Fairly easy to create one flag variable and to convert that binary text variable into flag variables. You don't have to use female. So this variable will flag females. You can compare it to male to flag variables. Same logic. That would be about, let's see, the flag variables. Okay. Any questions? Yeah. Let's see. Okay. Correlated variables. When the variables are correlated, the things will be trickier if the correlated variables are input variables. If the input and target variables are correlated, that is a good thing because you have identified a strong input variable that is informative about the target values. But if the input variables are correlated, that can be problematic. What does collinear mean, or what does a perfect correlation mean? The two variables have perfect correlation when the correlation coefficient is 1 or -1. It's perfectly collinear. When a variable changes, the other variable changes accordingly and in a perfectly consistent way. From a data science point of view, the two variables carry the same amount of information. That's when perfectly correlated variables happen. And to a model builder, that is not typically a good thing. Even though the two variables carry the exactly same amount of information, if you include both variables in the model, to the least, it will make the model unstable. The model will be confused about whether or not to prioritize one or the other variable. The model will be confused in numeric optimization process. It will create problem to finding a solution here. And the worst case is that sometimes the two variables are not. Sometimes the model didn't break, and the model seems to be doing well, but the two variables are kind of taking away the other less important variables in terms of the parameter improvement. So this creates sort of an illusion that these two variables become very, very important, but ultimately these two variables carry the same information. They kind of inflates this part of the data, but then undermines the other parts of the data. So either way, it's not good if it's perfectly collinear. The upper right chart would be the case where where two variables are perfectly linear. Their scatter plot will line up on a straight line throughout all the points. So that indicates that it's perfectly linear. When the correlation is not perfect but quite high, the points will line around a straight line, but not exactly on the line. Be scattered around, although not to a very large extent. So what do? Perfectly collinear input variables should not be included together in the model. So choose one of them. Computationally, it doesn't matter which one you choose, but ultimately we need to explain the results. We need to understand the result. So choose the one that is better to interpret and makes more business sense, and remove the other one if you are sure that the correlation is one or perfect. For highly correlated but not perfectly correlated variables, it's safer to retain both of them and later use other analysis to identify and to compare variable importance. You have much better tools than having to make a subjective judgment in terms of which one to retain. So that would be suggested. Anything that is not beyond 0.995, you can safely retain them both and later use other tools, as long as it's not exactly one. You can see that these data points do not look natural. These are simulated data. So in the Jupyter Notebook, you can see how these data points are simulated. Every time you generate a new sample, it will be slightly different points, because here I didn't implement the same seed. I didn't use the same mechanism to control the random draw. So if you run this creates 4 variables, x1 and 2, z1 and 2. x1 and 2 are exactly the same, so that's why they line up on the same line. But z1 is a random variable. z2 will be further calculated based on z1. That's why initially they are 0, but then z1 are replaced by a formula which has something to do with z1, but then adding some random components, right? So after these replacements, when you look at the correlation between x1 and 2 are 1, but correlation between z1 and z2 are not exactly 1, but quite high, 0.9. And when you make graph, the correlation one pair of variable will line up on one line, but the other scatter plot will look quite nice. It's high correlation, but not exactly collinear. Questions? Right.
When you say we need to avoid these variables when they have correlation about 0.995, like beyond 0.995, is it like a standard that we need to follow?
A sign? No, it's the absolute magnitude. Yeah. So correlation, the range of correlation is between -1 and +1, and the middle point is 0. So, it's these regions that should be fun. It's those extreme regions that you need to watch out for, including the extreme end.
So it's normally 0.995 and about that.
Yeah,
Consider.
something like that. Yeah.
Okay.
All right. Let's see. All right, the last part. So we'll not take a break because we're nearing the finish line today. Anyway, we'll talk a little bit about linear algebra, and these would be the sort of typical computation when you start coding for the Adeline model, when you implement the Adeline model. You will multiply vectors and matrix because that's more efficient. It's better than a for loop. It's way better than a for loop, and even makes less errors. And then I'll talk about the notation I use. I hope you have looked at the cheat sheets. They look kind of crazy at first with all those notations, but once we go over those, it will become quite nice. It will become handy when you are trying to implement a model. Those should provide a clear guide in terms of what to do and when to do what. Here, talk about the notations. So things that we will rely on, data wrangling, data pre-processing, is Pandas, mostly Pandas, sometimes NumPy. For matrix calculation, we also use Pandas sometimes, but NumPy are the engine behind Pandas in terms of matrix calculation. So they are the same thing. We also occasionally use, or quite often use, native operands. So what is this? When you say A star B in Python, what does that mean?
Multiplication.
Multiple.
Yeah, yeah, straightforward multiplication. However, if A and B are matrix or higher dimensional, and let's say A and B both are 3 by 2 dimensions, so that means both A and B have 3 rows and 2 columns. And when you do the star sign here in Python, what does that mean?
Matrix multiplication.
Well, yes, multiplication, but not exactly. It's not matrix multiplication. It's the element-wise multiplication. Does that make sense? So you can actually do that. In matrix multiplication, you can't do that. The columns and rows have to match, right? The inner dimension has to match. So for an illustration, in Python, the element-wise multiplication. So I will change the dimension to make it easier. It's both 2 by 3. And when you multiply A and B, it will take the values on the same position and multiply them and become something and put in the same place. So it's not 0, it's a placeholder. And it will take this, the values on the same position and put them in the same position. In the end, you'll get another matrix of 3 by 2, not 2 by 2. Make sense? So
What's that called? What's that called? It's not matrix multiplication. What's it called instead?
It's element-wise multiplication.
Thank you.
Yeah. So keep that in mind. We'll talk about matrix multiplication symbols there. But what is this? Double echelon. Can somebody tell me?
A power of b.
Yeah, raised to the power. Raised to the power. So 3 star 2 equals square of 3. In some of the programs, they use the pointy symbol, but not in Python. That means something different in Python. Anyway, so what's this? Slash? Slash? Somebody tell me?
Division.
Yeah, simple. And this is element-wise as well. Element-wise. For matrix. Okay. Let's see. Notations. These are matrix notations. I talk about summation. I or sometimes j. Mean. X bar. When we say bar, it's c. And these notations are used typically to describe a data point. And typically an I is there. It's not matrix notation, and it cannot be directly transformed to Python codes. To use Python codes, we need a matrix notation for easier translation. Observation and variables, not too much to explain, I think. A two-dimensional data set is like these. When I say an observation, we typically use I, and between 1 to I, and typically we use n to refer to the sample size, number of cases in the training set, and each I would refer to a row of the data set, a row. And the variables we use j typically, and we use m to refer to the number of dimensions of the input variable x. And this, we will keep using this n and m. N refer to sample size, number of rows. M refers to the column. Yep. Refer to the columns. So column. J refer to a column of the data set. We will use lowercase m to refer to the number of columns. So it's m columns and n rows. For dimension, I sometimes use n by m to denote number of rows and number of columns. I also use this notation, m, comma, m in a pair of parentheses to denote this is NumPy's. This is Python's output for dimensions. That's it. Matrix handwriting notations versus Python implementation are closer to those notations with summations and averages. Let's see. Let's use a motivating example here. You can run the codes in the Jupyter Notebook. The codes are already there, or you can open an online Jupyter Notebook engine, and you can copy these codes. We have two matrices here, different dimensions. A has a dimension of 2 by 3. B has a dimension of 3 by 2. So we can't element-wise multiply now. We can't do that. This won't work because both their rows and columns don't match. If their rows don't match but columns match, you can still use that to broadcast the. Sometimes you can use that you can use multiplication to broadcast the computation. But here, neither of these match, so code will break. That's why this will not work. So I assume linear algebra with some reflection, you know how that works. so I don't need to go too deep into that. Let me know if you need help. The book provides some additional resources in terms of chapters or textbooks. This book, put it before my face. See it. PML. There are different places where it provides resources about linear algebra. It's mostly matrix multiplication that you need to understand. In terms of taking derivative, you don't have to care too much of the steps because those results are robust. You simply use the results. It's a neural network that involves multiple layers, and we need to do the back propagation. That's when the most complicated sort of the matrix translation is involved, and that requires a little bit of patience and thinking. But we'll go through that without problem. So that's it for today. Any questions? We can use the 1 hour 50 minutes for questions if you have any. Great. So now we'll transition to. I didn't run the codes, but the codes are in the Jupyter notebook. Feel free to run it. The two matrices are the same. In NumPy form, and you can test. There are 3 ways to perform matrix multiplication. Right? You can use the dot function. You can use the @ symbol to implement the matrix multiplication, the inner product, and you can use the dot method of the arrays. I have updated the Jupyter notebook slightly this afternoon. So if you downloaded the Jupyter notebook before this afternoon or before today, you may want to update the Jupyter to re-download it. So that's it. That's it. Have a great night. Feel free to leave, but stay for questions.
I have a quick question. In my Jupyter notebook, I'm not seeing the headers like A, B are NumPy arrays. Is that normal?
Oh yeah. They are. I think that's the older version.
Oh, okay.
So they don't have to. I didn't remember. I made a mistake. I thought they have to be the series or data type, but they don't have to be data type. NumPy arrays have that method too.
Right.
Right. So all of these will work. All of these. Any other questions?
I have a question about a line over here. What does this line mean? Print hyphen multiply 20?
Okay. So that's interesting. It's a formatting line, and it comes in handy when you want to print several pieces of information in the same cell, but they kind of cluster together. But let me explain why that will work. Print is a simple print, so let me skip that first. That string variables are like a list. And with string variables or with list variables, you can quickly create multiple versions of that and put them together using multiplication. So, if I say super space times 5, so I get 5 super. So I can quickly print a long line of symbols without having to type all of them out. So that's what it does. So asteroid symbol with 100 asteroid symbol without having to type 100 asteroid symbol, I get 100 of them. So that's a quick trick.
Thank you.
Sure. Any other questions? No questions? So you guys just like the state? That's so great. Any other questions?
Yes, Professor. I have a question.
Yeah.
So as you said, if two variables are strongly correlated, one must be omitted. I totally agree. But when I was going through the textbook, I found a line which is contradicting this statement, which says in large data sets of which contains more than 1,000 rows. That's what it said. So in large data set, even the smallest 0.1 of correlation coefficient means it means that the two variables are significantly correlated, even if the
Right.
R value is 0.1.
Right.
So don't you think it? I think so. So on what basis should I eliminate the variables now? So even that's what I was thinking.
Okay. So I think the confusion is on. I think the book is trying to say a different thing. Let's see. So correlation coefficient, the magnitude is between 0 and 1. Statisticians or theoretical statisticists will tend to think that anything below 0.5 is not high because they have a region. A region for weak correlation is between 0 and 0.3 or 2. And medium region of correlation is between 0.3 and 0.6. Anything above that is high correlation. That is more that's more of a theoretical perspective. And I think the book that you're citing is more of a practical book. It refers to in real life data set correlation in large data set, particularly those data that describe human behaviors or live events. A correlation of 0.1 becomes significant. For one reason is that even though the magnitude is low from a statistics point of view, but the strength of correlation between the two events are quite meaningful. That's one part of the meaning. The other part of the meaning is that because of the sample size is quite large, over thousands of cases, the statistical power becomes larger. And if you do a hypothesis testing on the correlation coefficient, it tends to reject the null hypothesis of non-significance, which will give you a significant result. So either of these explanations could be true for the book that you refer to. I don't think that is something that's related to here. We are talking about highly correlated variables that will create a trouble in training the models. For input variables that have correlation of 0.1, never we have any problem including them both. So I think that the book is talking about a different thing, even though it's talking about correlation. And we are talking about training models that will be stable and without trouble. And we only have to deal with linearly correlated, which have a correlation of close to 1.
Close to 1, yeah.
Yeah.
Right. Yeah. Because I've seen this statement in the book Discovering Knowledge in Data, the book you've recommended.
Right. The context is different.
Yeah, the context is entirely different.
Yeah.
Right. Thanks a lot.
Sure.
Quick question, Professor Mark. This is like a general question. So I hear this argument where they say like machine learning is a glorified statistics or not. So many data scientists believe that it is not, or they argue that it is not. So I'm the algorithms that we have worked in all are statistic based. So how can you prove like it's not a glorified statistics, or any explanation that you have on that?
I didn't quite get the question.
So the expression where they say machine learning is a glorified statistics.
What statistics?
Glorified. It's just a statistics, but it's just given like
beautified. You mean beautified?
Yeah, kind of.
Okay, so fancy ways of presenting the same stuff.
Mm-hmm.
That's what's saying. So your question?
So there is, I mean, there is an argument on it. So data scientists believe it is not, and other people say no, that's what it is. So what do you think about it? Or
Okay, that I think it's definitely one of those debates. Let's see. Is data science more than statistics? That's the question. Well, for somebody who is, let's see, who is seasoned data scientist will not agree that. Okay, for a statistician who works with real life data set. So this person is a statistician, but he understands all kinds of problems with the real life data. The real life data a lot of times don't follow what the statistical theory predicts about how things will work. If this person is a seasoned statistician but also understands the real problems with statistics, with real life data, and also familiar with predictive modeling, but then he still claims that data science is merely statistics. I don't think that's quite likely. So I think the division is where real life data is involved. Oh, hold on. I think I'm more speaking from a business point of view, because so far we tend to we haven't leveraged the more advanced, more complex deep learning algorithm yet. I think at the mundane level, it's more of a real life situation, real life reality of the challenges in dealing with data that I think statisticians will not be comfortable with. So data science is more about data issues, data cleaning, understanding the data and the data issues. So that's the situation for business analytics. But if you think about computing, I think it's more data science. It's more of a difference. It's not as much difference between data science and statistics than computing and statistics. I think the computing side kicks in when it comes to those deep learning algorithms. Machine learning, which is part of computing that deals with deep learning, is trying to leverage machine to learn the patterns from the data. Statistics, even though it does contain all the possibilities that's discussed here in statistics, you can map out what's happening in statistics, but they have to make a lot of assumptions in statistics to be comfortably predicting the possibilities. Those assumptions does not have to deal with real life shortcomings, such as computing power or limitations of computers. They don't have to deal with that. They can make all those assumptions and eliminate all the real life problems away in terms of computation. But computer science is trying to make it happen. I think on that part, that's the difference. So in terms of theory, maybe there's nothing different. But in terms of implementation and make it happen, and not to say which one is faster, which one is slower. Simply on the part of making it happen makes a difference between stats and data science. That's my view.
okay, thank you so much.
Sure, it's an interesting question.
I had an argument with my friend, so I wanted your opinion on that. That's why.
Yeah. All right. Any other questions? Go ahead.
I do have a question, Professor.
Yeah, go ahead.
Okay, so
Is it you?
so why looking at them should put 20? Can you hear me?
Yeah. Your voice is a little bit slow, but I'm here.
Okay, maybe I hope it's better. So why the numpy random? So you all put a 20 for the number after the numpy random and the arrange.
Right. You mean which part is 20?
Over there. Let me double check. I think let me check my notebook.
So let me stop sharing for now.
It's a demo correlations.
Oh, okay. Let me go up. Yeah. Collinear.
No correlation.
Demo
Yes, this one.
Yeah. Oh, you mean
you
this
put a
20?
20 for all of those? So I'm not sure. Can I put another?
So here, what does 20 mean? 20 means the sort of the number of rows of data that I make. This is more like a sample size. I am simulating the data here. The first two rows, the first two variables are the same. I am creating a number sequence by using a range. So it starts from 0 with a step of 1. So 0, 1, 2, 3, 4, 5. I'm creating 20 of these values. So in the end, I'm getting between 0 and 19, 20 values.
So the 20 is a sample, even though you put a random, they only like pick up the 20.
But you have to keep them all the same across these 4, right? Because this is 4 columns of the same data frame, right? So you need to have the same. You can't have different numbers. It will create a table. It won't create. It will break. But you're telling computer to create a table with different number of rows on different columns. That would be not good. So something like this will not work, because to define the data frame, it has to have the same number of rows on all the columns. If that makes sense. So this won't work. This will break.
So it's just like I can just think like you choose the 20 samples.
Yeah. It's a convenient pick. Yeah.
Okay. I'm not sure someone actually have another question.
Sure.
PowerPoint. Okay, let me go and post my PowerPoint. Yeah. It's about flag variable.
Yeah.
So I just confused for page 17. So when k equal to 3, I know what's the 3 because there are 3 category. So k minus 1 equal to 2.
Yeah.
So what's the 2 points?
2 flag variables.
What's mean by 2?
It means.
So how can I show in the
So take a look at page 18.
18, okay.
Yeah. So using marital status as a variable, as an example here, marital status has 3 categories, right? Has married, single, and others. To create flag variables, we discard one of these. So we choose married and single. So in the slide, you see 2 columns here. 2 columns of flag variables. These are the variables that are created. The k minus 2, which equal to 2, refers to these 2 columns. And the values for these 2 columns will be according to the value of the marital status. So let's say if the marital status is married, then the column for married should be 1, but the column for single should be 0. That means this person is married. If the person is single, then the column for single, which is this one, the column for single is 1, but the column for married is 0. So this means that the value is single.
So can I think the two? Can I think two just like two attributes?
Yeah, you can think of that, but they are actually describing the same piece of information, right? So they are kind of a group of flag variables, which is a result of transforming the categorical variable. And after you transform the categorical variable, the original marital status will not be included in the training set. You know, so these two columns will replace the original categorical variable. It translates the textual categorical information into a numerical form for the model to be able to learn. Does that make sense? So yeah, you can think of it as eventually it becomes two attribute columns in the X variable.
Okay, that makes sense.
Yeah.
Thank you. That's all my questions.
Okay, great. Any other